In this video, we're going to look at the addition formulae or compound angle identities. We will look at the sine of a plus or minus b, the cos of a plus or minus b, and the tan of a plus or minus b. It's important to stress that trig functions are not distributive. If we take an algebraic expression, say 2 lots of x plus 1, we could write this as an identity, and that would give us now 2x plus 2. This is not the case with trig functions. So if we have now the sine of x plus 1, this is not equal to the sine of x plus the sine of 1. The easiest way to see this is using basic numeric values. So if we take now the sine of 90 degrees, the sine of 90 degrees is 1. We've seen this time and time again. So if we plotted this now in terms of the graph, y is equal to sine x, we'd have a maximum, and that would occur now at 90 degrees, and it would give us 1. So it would look something like so. This point right here is going to be 90, 1. There are lots of different ways I could write 90 degrees. I could write this now as the sine of 30 plus 60. And if we look at this using this particular approach, this would give me now the sine of 30 plus now the sine of 60. The sine of 30 is 1/2. The sine of 60 is root 3 over 2. If I added these together, quite clearly, they're not going to give me 1. It will give me 1 plus root 3 over 2. I could take a different approach. I could say now that this is the sine of 45 plus 45, which again gives me the sine of 90 degrees. Using that approach, sine of 45 plus sine of 45. The sine of 45 degrees is 1 over root 2, or if we rationalise it, root 2 over 2. Root 2 over 2 plus root 2 over 2 is root 2 over 2, which is not equal to 1, and it's not equal to 1 plus root 3 over 2. So we can see that this is not true, and that is the case for all trig functions. So if we got cos, if we got tan, if we got sec, cosec, cot, we don't write it like so. You'll not be expected to prove the formula, but you will be expected to use and apply standard results. So let's go ahead and look at those standard results. The first one we'll take is the sine of a plus b. So the sine of a plus b is given in the formula book, and this now is the sine of a multiplied by the cos of b plus the cos of a multiplied now by the sine of b. If we take now the sine of a minus b, this gives us now the sine of a multiplied by the cos of b minus now the cos of a multiplied by the sine of b. Or, if you like, you can say sine of a plus or minus b is equal to sine a cos b plus or minus cos a sine b. So that now is the addition formulae or compound angle identity for sine, and it is given to you. Let's now look at the cosine. The cosine is different. If we have cos of a plus b, this is going to give me cos a, cos b, and then we'll have minus sine a, sine b. If we have now the cos of a minus b, we're going to have now cos a, and then cos b, plus sine a, sine b. So this again is given, and it's something that you can quote and use. So for this, if you wanted, you could say now the cos of a plus or minus b is equal to cos a cos b minus plus sine a sine b. Later on we will go on to look at when b is equal to a and we have the double angle identities, and we will see the properties of those in a later video. With tan, let's write the tan. So the tan of a plus b, this is given now as the tan of a plus now the tan of b, and then we divide this now by 1 minus tan a tan b. And if we're doing now the negative, so we've got tan of a minus b, it will be very similar. So let's write this out. Tan of a minus b, we're going to have now tan a minus tan b divided by 1 plus tan a tan b. We might, in this particular case, be asked to show that using now the addition formulae for sine and cosine to write now that the tan of A plus B can be given in this form. So let's do that while we're here. But these are now the 6 results that you can quote. And these work equally as well with the reciprocal functions. So if you've got now cot of A plus B, you simply invert this and you can work like so. So lots of different approaches that we can use. So let's say now we were asked to show that the tan of A plus B was equal to this. So what we can do is use our identity. We know that tan theta is sine theta over cos theta. So tan of A plus B will now be an identity, and that will be sine of A plus B over now cos of A plus B. So let's go ahead and expand these. When I say expand, not in terms of multiplying them out, but writing them now as the addition formulae and working with them. So sine of A plus B is going to be sine A cos B plus now cos A sine B. So this might be a typical exam style question when you're asked to show that the tan of A plus B can be written in this form right here using the addition formulae for sines and cosines. So this now gives me the sine of A plus B. The cosine of A plus B is going to be cos A cos B, and then we'll have minus sine A sine B. What I'm going to do is divide the numerator and denominator now by cos A cos B. And you can often guide yourself through this. So if you look here, what we're aiming for is tan A. So what can I divide this expression by to get tan A? What can I divide this expression by to get tan B? What can I divide this expression here by to get 1? And that's where the cos A cos B is easy to see. So what we'll have then, and just writing this out, so we've got now sine A cos B divided now by the cos A cos B, so cos A cos B. Then we'll have plus now cos A sine B divided now by cos A cos B. And then this will all now be over cos A cos B, so I'm taking this part right here. So we've got cos A cos B divided now by cos A cos B, so cos A cos B, and then we'll have minus now sine A sine B over now cos A cos B. So let's see what cancels on here. So let's go ahead and write now that the sine of A over the cosine of A, that will stay. Cos B and cos B will cancel. Cos A cancel. Cos A cos B cancels. And now I'm just going to bracket this off. So what we've got here now is the sine of A over cosine of A, sine of B over cosine of B. So just tidying this up, we can now write, and I'll write it just here, we can say that the tan of A plus B now is given to be on here. We've got the identity, and this is going to be sine of A over cosine of A, which is tan A. Then we're going to have sine of B over cosine of B, which is going to be now tan B. And then we'll divide that now by, this one is just going to give me 1. And then we'll have now sine of A over cosine of A, which is tan A. And then we will have now tan B. So that's shown, and that's a typical identity that you might be asked to prove. Okay, so let's take a step back and go with our first example of the sine of 90 degrees. So let's now look at the sine of 90 degrees. So using now the addition formulae, we could write this as the sine, and I'll write it just here, the sine of 30 plus 60. That's clear, we could choose anything. The reason I'm choosing 30 and 60 are these are our special angles. So let's go ahead now and use this. So what we're going to do is say we're going to use sine of A plus B. So in this particular case, what we've got now is A will be equal to 30 and then B will be equal to 60. So using the sine of A plus B, we get now the sine of A cosine of B plus now the cosine of A multiplied by the sine of B. So let's go ahead and write this. So we've got now the sine of 30 plus 60. So I'm going to have now the sine of A, which is 30, multiplied by the cosine now of 60, that's B, plus the cosine of 30, multiplied by the sine now of 60. So all I've done is simply plug these in. So if we look, A is 30, B is 60, so I've put them in here. Sine of 30, cosine of 60, cosine of 30, now the sine of 60. The sine of 30 degrees is 1/2. The cosine of 60 degrees is 1/2. Then we're going to add to that the cosine of 30 degrees, which is root 3 over 2, and then the sine of 60 degrees, which is root 3 over 2. That will give me 1/4. That will give me now root 3 times root 3 is 3, so this will give me 3/4. If I add them together, we end up with 1. We know the sine of 90 degrees is equal to 1. So if you were asked to show using the addition formulae, all you do is plug the values in. You've got this in the formula book, you just need to identify A and B. And as you can see in this case, it doesn't matter which way round, in this particular example, you take it. In all of our work before, we've seen what we call special angles, and we saw these now for 30, we saw them for 60, and let's write them in order, 30, 45, 60, 90, and then multiples of these. We can use the addition formulae to find now exact values of angles that we don't know the special value of. So let's take an example here. Let's say we wanted to find now the cosine of 75 degrees. Clearly, working without a calculator, there are some that we can't do. But what we could say now is that this would be the cosine of 30 degrees plus now the cosine of, so cosine of 30 degrees plus the 45. So let's go ahead and do this. So what we've got here now, using the addition formula, we've got cos of A plus or minus B. So cos of A plus or minus B will give me cos A, cos B, minus sine A, sine B. And we've seen matches here. So what we'll do here, we'll say now let A be equal to 30 and B be equal to 45. So what we're going to do is sub this in. So we've got now the cos of 30 plus 45. So that will give me now cos of A, which is cos 30. And then we'll have cos 45 minus now the sine of 30 multiplied by the sine of 45. So cosine of 30 degrees is going to give me root 3 over 2. The cosine of 45 degrees is 1 over root 2, which I'm going to rationalise as root 2 over 2. Then we'll be subtracting away the sine of 30 degrees, which is 1/2, multiplied by the sine of 45 degrees, which is 1 over root 2, or root 2 over 2. So what have we got here? We've got now root 6 over 4, so let's look at that, root 6 over 4, minus now root 2 over 4. So if we put this together, we could see now as an exact value, the cosine of 70, let's put this in, root 2 over 4, the cosine of 75 degrees is going to be now root 6 minus root 2, so let's write this here, root 6 minus root 2 all over 4. And a couple of different ways that you could write that, but this is what we get. So let's check that on a calculator. Putting it in degrees mode, shift mode 3. If we now do the cosine of 75 degrees, that gives me now root 6 minus root 2 over 4. We could clearly show this with a range of different examples for the tangent function as well. Okay, let's move on. Sometimes we'll be expected to almost work in reverse. So we might be asked to rewrite as a single expression and evaluate, given now some expression. So for example, now let's say we had now, and we'll work in degrees still, let's say we had now the sine of 55, and then we had multiplied by the cosine of, let's go for 10, and minus now the cosine of 55, so let's put 55 there, multiplied by the sine of 10. After a while, you'll come to spot which format these are in. If we got a sine and a cosine here and a sine and a cosine here, it's going to be now the sine addition formulae or compound angle identity. If we got cos and sine, it's going to now be cos. So from this we can see that this is the sine. So if we look at now the sine of A minus B, we see that this now is sine A cos B minus now cos A sine B. So if we look at this particular format, what we can say here is that A will be equal to 55 and B will be equal to 10. So using this, we can say that this now is the sine of 55 minus 10. That gives me the sine of 45 degrees, and the sine of 45 degrees is going to be equal to 1 over root 2, or if we rationalise it, root 2 over 2. So what we've done is looked at this expression right here and sent it in reverse. We understand that the sine of a minus b gives us now these two expressions here. Therefore, we look at the values, we decide on an a and b, and we plug it in. So let's do a different. Let's say we've got now the cos. Let's go for the cosine of 20, and then we've got the cosine of, let's go for 70, and then we'll have now minus, let's say, the sine of 20, and then now the sine of 70. So which one does this look like? Well, we've got cosine, cosine, and then minus sine, sine. So this is going to be one of the cosine ones. With the cosine, the sign in between them is now different. So this will be cos of a plus b. So if we look now, what we can say is this will be the cos now of 20 plus the 70. So if we look now, if I expanded this out, I'd have cos a, cos b, and then we'd have minus, on here, yeah, that's right, sine a, sine b. So all I'm doing now is writing this. So we've identified that a is going to be equal to 20 and b will be equal to 70, or the other way around, it doesn't matter. So we can say that this is actually now the cos of 90 degrees, and that's going to end up giving us now 0. Cos of 90 is 0. And again, if you want to put this in a calculator, you can see that will be the case. Okay, let's do one with tan, as we seem to be neglecting tan a little. Say we've got, let's go for tan of, and we'll make this slightly harder, let's go for 28 plus now the tan of 32, and we put this now over 1 minus tan of 28 multiplied by the tan of 32. So let's go back to tan. Tan now of a plus b. So if you're unsure, when you've got a plus b, you're always going to have the positive in the numerator. This gives us now tan a plus tan b, and that's over now 1 minus tan a tan b. So we can identify now that a is going to be 28, we've got b is going to be equal to 32. So if I add those together, we've got now the tan of 60 degrees using a and b. So all I've done is use those. Now the tan of 60 degrees is one of our special angles, and we end up now with root 3. That's just working with some basic values. We're just subbing it into a formula that we're given, and we work on it. Let's move on and look at something slightly different. Say we're given now some angles. Let's say we've got angle A, and we'll say now that A is acute. So let's look now and say, so this is acute. Let's take B, and let's say B is obtuse. Okay, so let's go for B being obtuse. We might now be told that sine A, so sine A, so let's say sine A is equal to 3/5, and now cos, let's say cos B was equal to, let's go for minus 24 over 25. And we might be asked to now find the sine of A plus B. We might be asked to find, for example, now the cos, let's say cos of A minus B, and let's say now the tan of A, and we'll go for tan of A, and we'll do tan of A minus B. Okay, so these are just examples I've chosen. So what we could do is use some basic triangles with this. So if I now plot these, what I'll do, I'll draw two angles. So what we'll have an acute angle. So my acute angle is going to be A, which will look something like that. So these don't have to be wildly accurate. And then I'm going to have B, so let's go ahead and put B just here. Now with B, showing this as an obtuse angle, we can show it as an acute angle and simply use the property that the obtuse angle will be the same. So let's go ahead and do this. I'm not going to put them on the same axis here, as they're going to look a little strange. So this one is going to be 24 over 25. In fact, we could let's go ahead and put them on. Let's go ahead and put them on 1. And we can do that. So what have we got on this one? Cos B is 24, so minus 24 over 25. So it'll look something, again, not brilliant, but it'll give us some idea of what we've got. Okay, so that's what we're looking at. So all I'm saying now is essentially this angle B is going to be now the same as the obtuse angle. So let's label this up, and we've seen examples of this in previous units. So what we've got then is A. So A is going to be just here. This is A, and then we can put on B just here. So I've got A and I've got B. Now the sine of A is going to be 3/5. So we've got 3 and 5. Therefore, using our Pythagorean triple, that is going to be 4. This one right here, we've got now the cos of B. It's minus because it's now in the second quadrant. It's an obtuse angle. We've got 24 and 25, which means that this one is going to be 7. Again, that's a Pythagorean triple. So if we do now 25 squared minus now 7 squared, that's going to give us 576. The square root of 576 is 24. So a nice Pythagorean triple. So let's look at this. We know this is in the second quadrant. So we can say now that cos B will be equal to minus 24 over 25. We got now the sine of B. The sine of B is going to be positive, and that will be 7 over 25. That's just the opposite over hypotenuse, and we can say that tan of B will be equal now to 7 over the 24. That is the opposite over the adjacent. For A, we've got now, and I'll write this out, we've got cos A. Well, cos A is going to be positive, and it'll be 4/5. We were given that sine of A, again, all of these positive very acute angles, was 3 over 5, and we can say that tan of A is going to be 3 over 4. So let's now look at the sine of A plus B. So we now know that the sine of A plus B will be the sine of A, and just writing this out, sine of A cos B plus cos A, and then we're going to have sine B. So let's do this then. The sine of A, well, that's going to be 3 over 5 multiplied by the cosine of B, which is going to be minus 24 over 25. And then we're going to add to that the cosine of A, which is going to be 4 over 5. And we'll multiply this now by the sine of B, which will be 7 over 25. So what's that going to give me? That's going to give me now minus 72. So that's minus 72. So minus 72. And then we're going to have plus now 28. And that's all going to be over 125. So what's that going to give me? That's going to give me now on there, what are we going to have? Minus 44. So let's put that on. So minus 44 over 125. So let's write this in. So minus now 44 over 125. So that's now the sine of A plus B. We could see if I wanted to do now the cosine of A minus B. The cosine of A minus B is cos A cos B, and then we're going to have plus sine A sine B. So all we would do is sub in these values. So we'd have now 4 over 5 multiplied now by minus 24 over 25 plus the sine of A, which is 3 over 5, multiplied by the sine of B, which is 7 over 25. And we could go ahead and evaluate this without a calculator. So we'd have now minus 96, and then we'd have now plus, that's going to give me 21, and that's all going to be over now 125. So what's that give me? Minus 75 over, let's put this on, minus now 75 over 125. So that's going to give me now, dividing top and bottom by 25, minus 3 over 5. So that's what we get here. And later on we will look at some of these results when we go on to the double angle identities. So we can see now, if my calculations are correct, that that's going to be minus 3/5. As we can see, it can do exactly the same for tan of A minus B. I won't go through it all, but what we'd have now is the tan of A minus the tan of B all over 1 plus now tan A and then tan B. So the numbers that are going to go in are simply going to be tan A, which is going to be 3/4, minus now tan B, which is the 7 over 24. And let's put this on. I need to make sure these are negative, don't I? I've put them on as positive, so we need to just swap these over. Let's just switch these. Let's put my negatives on here. We've got the tan of B. Let's just put that in as a minus. So before I forget, that is a minus. So we'd have now the tan of B, which is going to be minus 7 over 24, and then we can have 1 plus tan A tan B, and you'd simply go ahead and multiply those. So do be careful. As you can see, I've forgot to put my negative on here. We know that the tan function is going to be negative in the second quadrant, and all of them are going to be positive here. So tan, let's put this here, tan and cosine are negative here, and then sine is positive there. So there we go. That's an example of using these given, if we're given now the sine of a single angle. The single angle here is A, and then we've looked now at these compound or addition formulae. We might be expected to solve equations using now these compound angle identities. So let's look at an example. Let's say we got now 2 sine x, and that now is equal to, let's go for x plus now 60 degrees. And we were asked to show using now the addition formulae results for x. So let's go for x, and we'll take x between 0 and 360 degrees. We could work in radians if you like. If you want, you could work in radians. We'll look at answers in radians. I'm just using degrees, as for many people, it's easier to see, especially if you're learning a new topic. So let's leave this alone. We've got 2 sine x. What we're going to have here now is the addition formulae. So we've got cos of a plus b. So in this case, let's let a be equal to x, b be equal to 60. So we're going to have now cos x multiplied now by the cos of 60 degrees. Then we'll have now minus sine x, and then we'll have now the sine of 60 degrees. So that's using the cos of a plus b. When we expand it out, we get cos a cos b minus sine a sine b. So let's work through this. We've got 2 sine x, and then now we've got cos of 60, which is 1/2. So I've got 1/2 cos x. So my cos x remains, but we can evaluate the cos of 60, which is 1/2. And then the sine of 60 is root 3 over 2. So we've got now root 3 over 2 sine x. Now, later on, we will look at an example of where we're given an expression like this, and we have to work it back and put it now as this particular cos of a plus or minus b, or sine of a plus or minus b. But we'll come to that shortly. But do keep your eyes on this, as now we will be expected to spot certain values. So let's just multiply through the equation by 2. So we've got 4 sine x, and then I'm just going to add the root 3 sine x to both sides, plus now root 3 sine x is going to be equal now to cos x. So that's what we end up with. So that's what we've got. So if we just factor this now, what I've got here is 4 plus root 3 multiplied by sine x, and that will be equal to cos x. So let's look now at solving this equation. We're interested in x between 0 and 360, and we can use an identity. We know that sine x over cos x is going to be equal now to tan x. So if I divide both sides by cos x and both sides by the quantity 4 plus root 3, we can say now that sine x over cos x is going to be equal now to 1 over 4 plus root 3. So all we've got to do is solve this. So what we've got then is tan x will be equal to 1 over 4 plus root 3. So let's go ahead and get a principal value now. So we're in degrees, so shift tan, inverse tan of 1 over, and then we're going to have 4 plus now the root 3. So that gives me 9.89 or 9.9, so let's just put 9.9. And then, of course, we're interested in subsequent solutions, so we need to, and we'll write it just here, x is going to be 9.9 degrees, and then we're looking now, we're adding multiples of 180, so it'll be 189.9 degrees, and so on and so forth. So these are the only two in the interval that we're interested in as we ask for x between 0 and 360. So all I've done is written out that x is equal to the inverse tan, and we would write that in the exam. We've got a principal value, so 4 plus root 3, that gives me 9.9, and I'm just adding multiples. If we needed to go backwards, we would just subtract multiples of 180. The tan curve cycles every 180 degrees, as we know. So let's just draw a quick sketch. If you are not happy with that, what we've got, if we look at the graph of tan x, we've got now coming up here, we've got the asymptote just here at 90, and then we're going to come back round, and this will cycle every 180 degrees. Or if you like, if you use now the cast diagram or unit circle, if we have now a value here, a principal value, by symmetry we've got one 180 on, as the tangent function is positive in the first and now the third quadrant. Let's just put a plus, there we go. So that's what we'd have. Let's move on and look at something slightly different. What we might be given now is an expression, and we might be asked to put it in the form of the addition formula, or now a compound angle. Compound is just adding A and B. So let's say we go back and we have now 1/2 cos x, and then we have now minus √3/2 sine x. So we looked at something similar to this in the last equation. If we consider I've got cosine here and sine here, and I've got now a negative between them. My choices are cos, and then we could have A plus B, as this is going to give me now, and I'll write this out, this is cos A, cos B, and then we've got minus sine A, sine B. The alternative would be now to say that this is the sine of A minus B. So in this particular case, we could write this as sine A cos B minus now cos A sine B. And we will look at the relationship between sine and cosine just here. So if we look at this, I could write this now. Looking at this particular approach, I could have that this was now 60 degrees. So this could now be 60 degrees. I know that cos of 60 is equal to 1/2. So I could write this now as cos of 60, and then we've got the cos of x, minus now the sine of 60. The sine of 60 degrees is √3/2, and then we've got now sine of x. So we could write this now, looking at this backwards, and this is one way that you could view this, that this is going to be now the cos of now x plus 60 degrees. And if you're unsure, multiply it out. Cos x, cos 60, and then minus sine x, and then the minus sine x, sine 60. Okay, so that's an example here. If we looked at it a different way, can we do it another way? Well, this value right here, if we take this now to be A, we could say that this, and I'll write it just here, this was going to be the sine of 30 degrees multiplied now by the cos of x, and then what we would have here now is minus, and consider what we've got here. We've got now the cosine of 30 degrees here, so we've got now cos of 30 degrees, so let's write that there, and then now we've got the sine of x. So let's see what this gives us now. We've got sine of 30, and then cosine of x, then we've got now the cosine of 30 and the sine of x. So we could write this now as the sine of, and then we're going to have 30 minus x. So this is another way to write it. We've got the cos of x plus 60, or now we've got the sine of 30 minus x. And there are lots of things that you could still do with this now, using the fact that sine is an odd function. So we can say that sine of minus x is minus sine of x. We can also see the relationship between cosine and sine. We know that sine x is equal to cosine of x minus 90, and hopefully you can see this relationship here. Clearly, putting this in different forms are going to make your life slightly easier whichever way round you go, but this is something that you hopefully should be able to spot. So for example, if we had now 1/√2 sine x, and then we had plus now, let's say 1/√2 cos x, hopefully now you can see one way of putting this. We know that the sine of 45 degrees is 1/√2, or the sine of pi by 4 is 1/√2, and the cosine is. So you could look to put that now in the form sine of a plus or minus b and cos of a plus or minus b. So if you like with this one, let's just rewrite that. Let's now write this, and we could do so many different things with this. Cos x, and then we're going to have now, and let's put 1/√2, and then we'll have plus sine x, and then 1/√2. So we could see this now could fall into cos of x, and then in fact let's just put it as cos of a minus b to begin with. We could have this now of the form, and that looks to give us now, let's put this in, we could have cos of a minus b, where a is going to be now x and b is going to be the 45. We know that the cosine of 45 is 1/2, sine of 45 is 1/2. So I could write this now as cos of x minus 45 degrees, or if I wanted it in radians, I could have cos of x minus pi by 4. And that's one particular approach that we could do with it. We could, of course, express it in terms of sines, but that gives you some idea of how you could look at that particular problem. As stated earlier in the video, this can extend now to what we would call the minor trig functions. So if we have sec, cosec or cot. So let's just look at a quick example of one of those. Let's say we were asked to evaluate now without a calculator sec of pi by 12. And we wanted to get a value for this. Now sec is 1 over cos. So what I could do is write this, and this is one way of looking at it. We could of course use the special, identities that we got, sec squared and tan squared. We could look at using that. Alternatively, I could write this now as 1 over cos of pi by 12. Now, what we want to do is use the addition formulae. So you might be asked to use the addition formulae to show or find the exact value of sec of pi by 12. So we've got cos of pi by 12. So I could write this as 1 over now the cos, and we could write this as pi by 3 minus pi by 4. Pi by 3 minus pi by 4 will give me pi by 12. So what I've got now is 1 over cos of a minus b. So if I just think about cos of a minus b, let's write this in. Cos of a minus b is going to give me now cos a, and then we're going to have cos b, and then we're going to have plus sine a sine b. So let's go ahead and do that. So what we're going to have then is 1 over, we got cos a. So we're going to have cos of pi by 3 multiplied by the cos of pi by 4, and then we'll add to that now the sine of pi by 3 multiplied by the sine of pi by 4. So let's see what we're going to get from that. So we've got now 1 over, so we've got 1 over, and we'll write this out. We've got 1/2 cos of pi by 3. Cos of 60 degrees is pi by 3. So cos of pi by 3 is 1/2. Then we've got now cos of pi by 4. So this is going to give me 1 over root 2, or root 2 over 2. And then we've got now the sine of pi by 3. The sine of pi by 3, which is sine of 60 degrees, is going to give me root 3 over 2. And then we've got now on here, we've got the sine now of pi by 4. Sine of pi by 4 is going to be root 2 over 2. So what's that going to give me? That's going to give me now on here, we've got root, let's put this here, we've got root 2 plus root 6. And that's all going to be over 4, which we can therefore put as 4 over this quantity. So expressing it like so, entirely up to you, that's one way of doing it. The other way is just to evaluate cos of pi by 12 and write 1 over that. So this is what we get, and if we were asked to now just rationalise it, we would just multiply this by the conjugate, so the root 2 minus root 6. And you could go ahead now, let's do that, root 2 minus root 6. So what's that going to give us? That's going to give us now 4 minus 6, which is minus 2. So we're going to have minus 2 lots of this quantity here. So let's just do that. So this is going to give me, let's write this out. We've got 4, and then we've got root 2 minus root 6. And then that's going to give me 2. So we've got 2 minus 6. So we've got now minus, this is going to give me now, what's that? Minus 4. So we're going to have minus the quantity root 2 minus root 6, assuming my calculations are right, which will be root 6 minus root 2. I'm hoping that my surds work has held up. Let's just check that on the calculator. Let's put it straight in. So let's switch this up now, pi by 12. So we'll put this now in radians, shift mode 4. Hopefully that was a fair explanation. I was kind of thinking what I was doing as I was going through it. And I'm getting quite tired as I go, but hopefully that will make some sense. So let's see what we end up getting. And then we got root 6 minus root 2, which is that, which is fair. So it might be a slightly quicker way of doing it, but essentially all you're doing is the addition formulae. You'll be asked to use the addition formulae to show that's the case. Let's just finish off with some identities. Now, in the first part of the video, we looked at the identity to show that tan of a plus b could be written in the form using sine of a plus b and cos of a plus b. We'll just look at one more. Now, we know a standard result could be the cos of 90 minus theta is equal to sine of theta. So this, let's just write this here. So let's say the cos of now 90 minus theta is given to be sine theta, and that now is a result that we know. If you wanted to view this with a triangle, you could just go ahead and look at a triangle. So if you now look at this particular triangle, we've got now theta. So if we put theta here, we've got now this is going to be 90 minus theta, and then we've got the right angle, and we can see that the cos of 90 minus theta is going to be equal to the sine of theta, and that's something that we've already seen. But we might be asked to use the addition formulae to show this. So if we're working now with any trig identity, we start on the more complicated side. The more complicated side is the left hand side. So what we're going to do is use now the compound angle identity for cosine. So what I've got is a cos of a minus b. So I'm going to have cos now of 90, and then we're going to have cos of theta, and then we're going to add to that now the sine of 90 multiplied by the sine of theta. Now if we look at the cos of 90, and if you just want to sketch this up, the cosine of 90 degrees is going to be 0. Okay, so hopefully you can see that this is a fairly straightforward identity. So we'll come up and do something like that. So that is now 90 degrees, and we get 90 naught. So what we can say is that this is going to be naught plus now the sine of 90, which is going to be 1, multiplied now by the sine of theta, and that gives us now the sine of theta. Therefore, the left-hand side is equal now to the right-hand side. You might be asked to do something different. So that's a typical example. Let's just look at one more. Let's say we were asked now to show, let's do the sine of a plus b minus now the sine of a, and we'll go for a minus b, and we'll show now that this identity gives us, let's say 2 sine a cos b. From memory, that should work. So let's go ahead. We're going to have sine a cos b plus cos a sine b minus, and I'm just going to put this up here, minus, we're going to have now sine a cos b, and then we're going to have here minus cos a sine b. So again, I'm working now with what seems to be the more complicated side. So what I've got here now is the following. I've got, if we just write this out, I've got the sine of a cos of b, and then I'm going to have now minus the sine of a cos of b, and they're going to cancel. Then I won't show the full workings, you need to show the next few lines. We got cos of a sine of b minus cos now of a, and then the sine of b. So you can see that these are going to cancel, and this is just going to give us now 2 lots of the sine of a, the cos of b. Clearly you'd have to show that next line in your workings, but you can see how that's going to work out to give us now 2 sine a cos b. So there we go. That's a brief introduction now to the addition formulae or compound angle identities. Hopefully I've not made any slips because I've been doing it as I go, but using the formulae that you're given in the formula book, you're simply expected to plug values in and have some idea. In the next video we will look at double and half angle identities.